Hi, this is Chapter 9, Process Improvement and Six Sigma. We're going to start talking about process improvement methodologies, which essentially all of them do these things, which is define the problem, analyze the problem, generate ideas about how to solve the problem, evaluate and select one of those ideas, all of those ideas, and select one of them, and then implement the idea so that you can bring about process improvement. Deming, at the root of all of those is essentially the Deming cycle. Now, Deming created this wheel. They call it also the Deming wheel, and it's plan, do, study, and act. And as you can see, at the heart of it is the customer satisfaction. This actually started by Walter Short many years ago, but then Deming sort of modified it, and he said, when you have, to go to production, you must design the product with appropriate tests. Then you need to make sure that the product is going to do what it's supposed to do. So for that, you need to test it on the production line and in laboratories. Once you know that the product is what it should be, and it does what it's supposed to do, then you sell the product, and then you'll continue to monitor through market research and all that to make sure that the customer is happy. So that's essentially the Deming wheel and the Deming cycle. Japanese changed it a little bit, and they called it Plan, Do, Check, Act instead of Plan, Do, Study, Act. Now there are several steps to the plan phase or to the plan part of the Deming cycle. The first thing that you must do when you plan is to define the process from start to finish and make sure that you know what it does so that then you can understand it and improve it. You must describe the process, all of its key people, what it does, all the steps in it, equipment used in it, any conditions that must not be violated when you run the process, work methods, materials used, etc. You must describe the players in the process who are both the internal and external customers of it, and who also are the operators in it. Define the customer's expectations, what the customer wants, when he or she wants it, or when that internal process may be that is an internal customer to the production. When, where, all of that needs to be defined. Determine any historical data that may be used or any new data that we must collect. Describe the perceived problems with the process. So for instance, we cannot meet customers' expectations, or there is excessive variation, or it takes too long to do something. So all of those are problems that the process may be having, and we need to be able to identify it so that we can resolve it. Once those are done, then we must identify the primary causes of the problem, and how they will impact the process, and how can we remove those. And then develop potential changes or solutions or strategies to get rid of the problem or to resolve the problem. And then once a method or a solution is selected, then we must implement it and make sure that it's the right solution. In the do phase, we identify measures or metrics, so to speak, so that we understand how the changes or the solutions are in fact gearing up against what we expect them to. So this is very important. It's part of the scientific method of doing analysis because you need to identify your measures first before you do a pilot study or an experiment or a test to be able to gauge the process against those measures. In the study phase, we examine the results of the pilot study or the experimentation that we've done. We determine whether the process and its performance was improved and whether more tests, more studying, more experimentation is necessary. And then we act by selecting the best of the changes or the best of the solutions or process improvements that we have identified in the previous stages. We develop an implementation plan around it, standard operating procedures, um, any training that must be provided, any standardization that must be done. All of that is completed in the ACT stage. And essentially, we must create all the right environment so that the process can be monitored and controlled on an ongoing and stable basis. So, all of this requires creative problem solving. And as your book says, really creative problem solving doesn't need to be too fancy. A lot of the time, the people who work for you, the employees who work with the process and do the work, really know how to bring about improvements. Toyota has been known to say that they have, their employees create 1.5 million suggestions per year, and 95% of them are implemented or in some way, shape, or form put in use. So creating ideas for solving problems or generating ideas for solving problems is not usually an issue if you tap into the talents of your and the knowledge of your employees. But there is a process that can be followed so that we are consistently using problem solving, and that starts with understanding the mess. A lot of the times, the people might think that something is a problem, but it's really not. It's a symptom of the actual problem. So we must understand all the symptoms, find all the facts, identify the actual specific problem, so do a root cause analysis, generate ideas, and that is best done by brainstorming, including people who are affected and who are in the process and do the process and operate the process, and get them to brainstorm and generate ideas, develop solutions, and then implement those solutions. So there are several methodologies that have been built around this PDCA or PDSA concept. One is called FATE, focus, analyze, develop, and execute. Another one is DRIVE, define the problem, recognize the cause, identify solutions, verify the actions, and then evaluate the results. And some organizations actually embed the Deming cycle in their framework, in their process improvement framework. So, for instance, here, once you go through the process and you're at the point where you must generate ideas, then it kicks in, the Deming cycle kicks in, and you can do the PDCA and end the process and find, hopefully by then you will have found your improvement or your the method that will decrease variation or make the process lean or whatever it is that you started out for. So one methodology for the PDCA essentially is based on PDCA that is used in Six Sigma is called the DMAIC. and that stands for define, measure, analyze, improve, and control. So in this PowerPoint set and in this video, we will be talking about that. So Six Sigma, what is Six Sigma before we do the make process? What is Six Sigma? Well, Six Sigma is a philosophy of bringing improvements to business processes. It's a way of thinking essentially, which seeks to find and eliminate causes of defects. More often than not, that causes a variation that we're trying to get rid of, so that we can reduce defects and errors in manufacturing and in service processes. And Six Sigma does it by focusing on outputs that are critical to the customer. So again, customer is at the center of this whole analysis. Just like let me show you the Deming cycle again. This is the customer is at the center of it, right? And so that's what we're talking about. Six Sigma tries to do that, tries to eliminate causes of defect and error with the customer being at the center of the focus, and having financial return for the organization. So that bottom line is the focus, and there has to be some financial justification for doing the Six Sigma project. The term Six Sigma is based on statistical measure of having 3.4 or fewer errors per million opportunities, or DPMO. And so Six Sigma as a discipline or as a philosophy, it tries to reduce error, but the Six Sigma with, written, if you write it with lowercase s, then it is that statistical measure, that statistical way of analysis that equates to 3.4 defects or fewer defects per million. Six Sigma started in 1980s with Motorola being the charging company essentially, and they had certain goals that they had set for themselves to achieve, and by mid 1990s, General Electric jumped on board, and since then the rapid growth of Six Sigma and the interest in it has been astounding. The principles of Six Sigma are very specific. The first principle is that we need to think in terms of key business processes and aligning them with customer expectations and customers' needs. So that strategic objective of making sure that what we do is for the customer, and the way we run our business is to achieve customer satisfaction. That's one of the basic principles of Six Sigma. Another one is focus on corporate sponsors, so that we have individuals within the company who champion the success of Six Sigma, and they will try to overcome that resistance to change that is in any organization, and also to obtain resources so that Six Sigma projects can be implemented. Another principle of Six Sigma is to emphasize quantifiable measures, quantifiable measures that can be used across the enterprise, the organization. So that, for example, defects per million opportunities, DPMO, can be used within any given function. It would have its own flavor, but You can use it for manufacturing, for engineering, for software development, for administrative duties, for any of those. So it's a measure that anybody and everybody within the company can identify with. Um, Another principle is ensuring that the appropriate metrics are identified early, so that everyone involved within the process can uh, have they would know what their expectations are of them. And this by itself produces incentives and encouragement for the individuals, for the employees to aim to achieve that standard, that measure that is the ultimate goal. Also, extensive training must be given to everyone involved, so that waste can be reduced. Non anything that is not value adding can be removed from the process. Any activity that is wasteful can be removed. Cycle times can be reduced, etc. Another principle is create highly qualified process improvement experts. So all those belts, green belts and master black belts or black belts, and all of those individuals should be trained and retained within the company so that they can not only help to improve processes and apply those process improvement tools, but also to lead teams, Six Sigma teams, and be able to coach and provide training and guidance. And finally, set stretch objectives for improvement. And by that, we mean that we need to have SMART objectives. And by that, we mean S for for specific, simple, sensible, something that is significant, but it makes sense and it's simple to understand and simple to identify. And M for measurable, meaningful, motivating objective. A for achievable or agreed or attainable objective. R for relevant, reasonable, realistic objective. And T for time bound, something that's timely, something that is not so overwhelming that it takes forever and ever and ever to do. And so you need to have an objective that or a, a, a problem that you're trying to solve that can be done incrementally with achievable outcomes. So the differences between Six Sigma and TQM, people in charge in a TQM system are actual workers that are being empowered, whereas in Six Sigma, it's the actual business leaders that are championing the Six Sigma projects. Activities in TQM occur in functional units or processes or workplaces, but in Six Sigma they're cross-functional and they span all of the organization. Training is in TQM are simple improvement tools, but for Six Sigma they're rigorous, advanced statistical tools, and also the DMAIC methodology. And from a financial perspective, TQM really doesn't have much to do with, it doesn't require financial accountability and improvements. So from that perspective, TQM is a little nebulous as to what is the purpose of it. Whereas with Six Sigma, there is clear focus on bottom line, and you need to have verifiable return on investment when you're doing a Six Sigma project. So the whole theory of Six Sigma goes is based on how many standard deviations of the process can we fit within the tolerance range, within the specification limits that the customer imposes. So in this view graph, you can see that if this is the target, and if this is from here to here is the tolerance of the customer, we are able to fit six, or the process is, the standard deviation of the process is such that six standard deviations can fit from the target to the lower spec limit, and six standard deviations can be fit or is contained within the target, between the target and the upper spec limit. And so when you have that kind of an occurrence, then you can say that you're operating within Six Sigma. But we always want to allow some shift or some adjustment, because we know processes are not absolute, and so they will move, and they will there is variation within them, and even the center of it is going to shift due to processes, man, machine, method, materials, and all of those M's of the of manufacturing. And so when you have this situation, the standard rule is to allow 1.5 standard deviations for shift or for adjustment within the process. So when you look at it, if K is a constant, or is the number of sigma levels that we have within a process, then that times the standard deviation should equal the 12 sigma that we have from lower spec limit to upper spec limit, the 12 sigmas divided by 2. Divided by 2 because we're looking at half of the range. So with that, there are a couple of examples in your book that I'm not going to cover, but here's a reserve 9.1, and it says Ultra Precision Corporation has historically had processes which operate above the 5 sigma level. They operate above the 5 sigma level. They have a new process on which they are about to start production. If the specification for a critical part produced by the process is 3.5 centimeters plus or minus 0.1 centimeter, and the standard deviation for the process is 0.019 centimeters, at what sigma level is this process operating? So in here, because we have 3.5 plus or minus 0.1, then we know our lower spec limit is 3.4 and our upper spec limit is 3.6. And if the process standard deviation is 0.019, then using the equation that we just reviewed, we know that K times the standard deviation of the process equals the tolerance. I'll just write it as tolerance divided by 2. And so in this case, K is the sigma level of the process. So in this case, we have 0.019, which is the standard deviation of the process, times K, equal to the tolerance of the process. In this case, we have 0.2. This is the difference between these, is 0.2 divided by 2. And so solving for K, we get 5.26. So historically, they've been operating at 5 sigma level, and now they're operating above 5 sigma, and so the process is fine, and there is no room for concern if 5 sigma level is acceptable for them. Here's another problem. Um, Nodro, whatever, cell phone company advertises that 99% of their customers' calls are completed without interruption. How many DPMOs, or defects per million opportunities, does this claim represent? So the defect rate is, if it's advertises, if it's 99% of the calls are completed, then the defect or the error rate is zero point zero 0.01, or 1 minus 0.99. So 0.01 times 1 million is equal to 10,000. So the DPMO is 10,000 defects per million opportunity. Now, at what sigma level is the process operating, assuming a 1.5 sigma offset, or 1.5 shift? So here we would use the norm inverse, norm S inverse. So if you were to type norm dot S dot inv in Excel and put 0.99 and then add 1.5 to it, you will get that sigma level that the process is operating in, and that gives you 3.826. The DMAIC methodology to define, measure, analyze, improve, and control have certain tools of quality that can be used with any one of these different phases of the DMAIC. For example, in the defined phase, there is a project charter that essentially it's the rules of what it is that you want to do for this particular project. So the project charter can be written. The cost of quality analysis must be done. How much is it costing us right now? How much improvements do we want to accomplish, etc. Pareto analysis, high-level process mapping. And so if you were to read this this table, you will see that several of the tools that we have already studied in this class are listed here. The Ishikawa basic 7 tools of quality are also were listed among this in this table, and these tools may be used in a logical order. So note that this is only a typical order for use, that there's no hard and fast rule that they must be used in this fashion. But this flowchart sort of gives us the sequence of how any of these tools could be used. So in the early stages, you do want to have a process map, and then from there you will do some check sheet where you can identify the sources of error or defect, and then you can use either histograms or control or scatter diagrams, scatter plots, or control charts to be able to control and manage the process. You will be able to then use all of that in a cause and effect diagram so that you can identify the true sources of mistake or error, and then you can do a Pareto analysis so that you can see which one of those it has highest impact on the outcome or of the performance of the process. So this is just a guide, but not necessarily something that must be followed in detail. So let's go through the different phases of DMAIC. Define describes the problem in operational terms. You must have a project scope. You must apply Pareto analysis, identify the SIPOC process, and to develop a SIPOC diagram, and essentially get a handle on what the problem is that you are trying to improve. So to show you a process map, Jack Frost has used his belt-driven hand-guided snowblower to clear his driveway for several winters. Due to a knee replacement, he can't do the work this winter. He wants to make a flowchart to assist his 15-year-old son in knowing what steps to follow when he takes over the job. Assume that the blower is stored in the garage. Some of the steps would include getting it out of the garage, blowing the snow off of the driveway, putting it back in the garage, etc. Are there other steps that should be included in order to have a more complete flowchart? Construct a flowchart using Excel or some other type of drawing tool, which I can tell you that in some of the resources that I will provide in Canvas. So here is an example. I don't know if you can see this, but I can zoom in. So we have oops. All right, better get in here. So we must decide that the driveway must be cleared of snow, so that decision must be made, and then open the garage, take out the blower. You need to decide, does it need fuel? If it doesn't, then that's fine. If it does, you need to get fuel, fuel the tank, and then decide, does it need oil? If not, then you can go ahead and start snow blowing. Otherwise, you need to get the oil, fill the oil, and then start snow blowing. And when it's done, you or you blow the snow away. You start it. You start the snow blower, and then you blow the snow. You turn it off. You decide, does it need to be cleaned or not. If it doesn't need to be cleaned, you park it in the garage and you close the garage door. But if not, if it does need cleaning, then you get the supplies, you clean it, and then you store it in the garage. So this is a process map, and it's not a detailed process map, but it is a process map. Pareto charts or Pareto analysis. Pareto analysis are developed based on Pareto distributions, which are essentially driven by the 80-20 rule, Pareto rule, that says that 80% of your problems have 20% of the causes are causing 80% of the problems. You can do a detailed Pareto chart where you can see that in view graph A, you decide what assembly has the most defects. And so is it assembly 5 or 2 or 1 or 9? And so you can see that 5 has the highest. And then you decide, what is the most common type of defect? Is it electrical? Is it assembly? Is it soldering? What is it? And so let's say that you have identified that electrical is the most frequent. Of a SIPOC where for a manufacturing company where the suppliers are the metal fabricators and component suppliers, the inputs are stamped parts and parts and subassemblies. Then the process includes body fabrication, painting, and assembly. Outputs are the finished automobiles, and the customers are the dealers. So for any of these, then we can have detailed components or maps drawn out where if there is anything wrong with, let's say, with the metal fabricators, with the way we do business with them, or with what they provide us, then we can do further mapping and do some and then later on do some root cause analysis. So erase all this. Um, for measure, we focus on understanding the process performance and collecting the data that is necessary so that we can understand that process. So key data collection questions are what is it that we're trying to answer? What type of data do we need in order to answer those questions? Where do we find the data? Can the data provide can the data be provided to us, or can we do it, who is it who can collect the data and give it to us, and is that individual trained to do that? How can we collect the data with minimal effort, and how do we do that? So all of these are operational questions that we must have in order to be able to measure the process, whatever quality characteristic is that we are trying to measure. Generally, run charts, checklists, descriptive statistics, measurement systems analysis that we studied in a previous chapter, all of these, capability analysis, all of these are done in the measurement phase. And you do all this so that you can benchmark the process, so that then when you later on have achieve an improvement, you'll be able to gauge and see how much improvement have you attained. Six Sigma generally uses the notion of a function in mathematics to explore the relationship between how the process performs and what the customer wants. And so let's say that a critical to quality characteristic that we want to have, or that we want to achieve, is 80% effective utilization. So from there we say, well, what are some things that contribute to effective utilization? Well, equipment utilization, rate per cycle time, and and the first pass yield. All of these are contributing to effective utilization. And so for each of these, then we can identify some measures. So, for example, maintenance downtime, changeover time, availability of crew, all of these would contribute to equipment utilization, which in turn affects effective utilization. So all of these then become our independent variables, or those factors that contribute to our achieving our intended goal. Check sheets are special types of data collection form, and they generally are used more than anything to collect data so that we can build histograms and Pareto charts with them. So here are some examples checklists. For this one, you can see that the frequency is listed here. You create ticks, and you have dimensions. Various dimensions are counted. Here's an example of an attribute where surface scars, cracks, incompletes, mishaps, etc. are recorded. And here we have a bubble investigation checklist where let's say we have something, a board or something that we must create, but then we mark on it how big the defect was, or how many there were, etc. In the analyze phase, we must start by understanding what the problem really is. And again, this is where the maybe an expanded version of SciPoc can be helpful, or maybe even an expanded process map, which we generally call value stream map. So a value stream map is a process map essentially, but it adds, it highlights or it identifies value added versus non-value added activities, including time that it takes, tack time, cycle time, all kinds of measures of whether or not an activity is value adding or it's not. And so because of that, value stream maps are generally a tool used in lean strategies and lean environments. It's important to know why defects or errors or excessive variation occurs. Generally, it's because of a lack of knowledge about how a process works. Um, it could be the lack of knowledge about how the process should work. So we don't, if we don't know where we should be, it's going to be difficult to get there. So that's essentially what we mean by that. It could be as a result of a lack of control of materials or equipment that are used in the process. It could be inadvertent errors in performing the work by the employees. Waste and complexity generally adds to defects and errors and variation. When you design quickly and hastily without thinking of all the production parts and equipments and how everything integrates into each other, you could suffer excessive variation or defects or errors. And failure to understand the capability of the process and how to meet specifications is also another reason. Lack of training for the employees, poor instruments, calibration, poor testing, essentially not doing measurement systems analysis well could contribute, and inadequate environmental characteristics like lighting, temperature, humidity, noise, etc. All of those. Root cause analysis is another form of analysis that we use in the DMAIC process. A root cause is essentially a condition or a set of conditions that if you identify it and if you remove it, then subsequently the product or the service that is generated is going to be free of defect and it's going to be considered good and acceptable. So root cause analysis is a statistical quantitative approach, and you use it so that you can understand the root cause of the problems and be able to identify it and remove it. So your book talks about the 5 why technique, and that's essentially nothing more than asking 5 times why. Remember in here, in this slide, we went through, let's say, 4 rounds of it. And essentially you say, why? Why is this happening? Why is this happening? Why is this happening? And in each set of why, you're honing in on the cause closer and closer. So, where was I? There we go. A cause and effect diagram can be used for doing root cause analysis. It's also called fishbone diagram, and also scatter diagrams can be used to do root cause. So here's a fishbone diagram. Essentially, you have it looks like a fish, right? You have the head, you have the skeleton, and you have all these little bones that come out. So here's an example. Wobbling saw blade. So That is the wobbling saw blade is the actual problem, but then we try to reduce it down to people or man, machines, methods, materials, and within each of those, then we try to identify a possible explanation. For example, for materials, it could be that the wood is wet and we can't saw it properly. It could be that the wrong size washers are being used, or it could be that the axe hole is the wrong size. So this is root cause and effect diagram, and here's another example from your book. To improve, you need people. I mean, in every stage you need people, but to improve, you really do need people, and you need them to brainstorm and be able to consider all the different options and all the different solutions or all the different alternatives that you may have arrived at, and then be able to evaluate and select. So some kind of a scoring model generally is used where you have different criteria that you gauge or you compare the different solutions. It could be the criteria could be economic, it could be people, impact on people, it could be the, 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 the the appropriateness of the process for the customers' expectations. It could be a number of things, and then for each of these criteria, you will have some kind of a scoring model or a scoring system where the different alternatives will be rated. And finally, for control, you would use checklists, control charts, standard right SOPs, standard operating procedures. You do all that so that you can make sure that the process that you have improved and the progress that you have made can be maintained. So the main goal of the control phase is to maintain the improvements and to putting tools in place that would guarantee that you can keep those improvements in place. There are also, your book talks about the managerial tools. Those are the new 7 tools of quality improvement. Those are affinity diagrams, interrelationship diagrams, matrix diagrams, tree diagrams, prioritization matrices, process decision program chart, and activity network diagram. So I'm not going to go through all of these, but the remainder of these slides essentially take you through that and a couple more. For example, not that one, but this one, for example, is a spider chart where you can quickly see how different metrics compare to each other in terms of having achieved what you set out to achieve. For instance, if the goal is the solid line, then you can see that metric A we fall short. On metric E and D also we fall short. Metric F we have outperformed what we set out to do, and for also B we have we fall short. We have not achieved the goal. And metric C, we have achieved the goal right on the mark. We haven't overachieved or underachieved it. So that's the spider. That's the spider chart. So there are other charts that I have here, and that's essentially the the Six Sigma process and the DMAIC process in a nutshell. Thank you.